Hello everyone. Today I'll be introducing the Lost Hiker drone system for the Introduction to System Engineering class. My name is Michael Scott, and with me here are Dian Su and Contessa St. Clair. The Lost Hiker drone system is a specialized solution which is designed to assist search and rescue teams in locating missing hikers quickly and safely. So we're going to go over a little bit about the purpose and mission objectives and the system overview of the Lost Hiker drone system. So to start, this system is designed to quickly detect and locate missing hikers in a wide variety of remote and rugged and difficult terrain to support law enforcement and search and rescue teams. Its core capability is it will be equipped with advanced sensors and cameras for terrain scanning and visual confirmation, and it'll use onboard intelligence to enable autonomous navigation and flight through dense woods and difficult terrain environments. In doing so, the system is built to operate in harsh weather conditions, handle the rugged terrain, like I mentioned before, the dense forests, and maintain communication even in areas with poor connectivity or low to no infrastructure, like what we would find in national parks or other remote regions. All in all, these features make a very powerful tool for a rapid and safe rescue operations that will support our rescue teams. So this slide is going to talk a little bit about our stakeholder needs for the Lost Hiker drone system. So our primary need is to reduce the time it takes to locate a missing hiker, which can be critical for their survival in remote regions. We're also aiming to expand the search area without requiring a proportional increase in manpower, which makes operations a lot more efficient. In the past, we've had a lot of operations that require a lot more manpower every time the search areas increase. So this was attempting to mitigate for that. Another key need is to provide real-time visual and thermal data to park rangers, which will enable faster decision-making and better information gathering. And finally, by using drones, we're going to reduce the exposure of our rescue personnel and our law enforcement to hazardous terrain and severe weather, which will improve the overall safety during these operations. So this slide illustrates the overall context diagram for the Lost Hiker drone system and how it's going to interact with various key elements during a mission. So at the center of the diagram, we have the drone, which communicates with the operator and the command center to receive its various mission goals, relay location, navigational data, and various updates, so on and so forth. The rescue team shares and receives data for physical recovery, while the Lost Hiker, which provides detectable signals like heat signatures, which is detected by the Lost Hiker drone system. There's various environmental factors, such as the weather and terrain, and it might influence various flight conditions, energy, signal data, so on and so forth. And we also have here critical interfaces, talking about the command and control data, video and thermal imagery, and location coordinates, where it's sending all this stuff along with energy transfer for charging or refueling at home base. The purpose of this context is to ensure that we're understanding all of the external elements that connect with our system and the data flows that enable the successful operation of the system. So this slide is going to outline the key high-level operational requirements that define the Lost Hiker drone system in order to achieve its mission. These requirements are setting the foundation for various metrics like system performance, safety, reliability. They cover aspects such as the autonomous search capability, human detection under various conditions, endurance for extended missions, real-time data delivery, and resilience in challenging environments like rain, fog, or wind. Additionally, they're going to talk about securing communications over long ranges, quick deployment by a single operator use, and features like an automated return to base and mission data recording system. Overall, these requirements are going to guide our design and our testing process to make sure that the system is going to meet the needs of the search and rescue operators as outlined in our stakeholder requirements. So building upon the operational requirements we just discussed in the previous slide, this slide is going to focus on the derived requirements. which are going to be our more detailed specifications, and they're going to use exact numbers that break down the high-level goals into more actionable elements that will drive our design. As an example, if our lost hiker drone system will autonomously search an area, the derived requirements are going to define how executing pre-programmed scanning sequences, all operator intervention will actually work in practice. Similarly, our detection requirements are going to be refined to include thermal signature identification, distinguishing humans from wildlife with high accuracy, and we're going to have actual numbers associated with each of these as well. Like I said before, each of these requirements are going to ensure that the system's capabilities are measurable and verifiable, and will bridge the gap between our concept of operations and the actual implementation of our system. And this is a very critical detail when we're talking about actually guiding our design decisions and ensuring compliance during test phases. So continuing from our previous slide, we have the additional derived requirements that are further going to refine our system's performance. We have the remainder of our operational requirements derived here. So talking about including stability in windy conditions, ensuring secure and reliable connection and communication, enabling autonomous return to base functionality. And we're also going to address quick deployment, automated system checks, data storage for post-mission analysis, and so on and so forth. The key takeaway here is that, like I said before in the previous slide, these requirements are going to translate our high-level goals from our concept into precise design elements and features that guarantee our mission success and alignment with our stakeholder needs.
Moving on to the mission scenario. The mission scenario describes how the LHDS is used. First, the park rangers receive a report of a missing hiker and identify a probable search area. The rangers prepare the LHDS, upload the search plan, and launch the drone. The drone flies an automated search pattern while collecting video and thermal data. Potential targets are detected on board and by human operators in the command center. When a target is detected, the system focuses on that area and captures more detailed imagery. Rangers then confirm whether the target is a lost hiker. If confirmed, the drone can communicate with the hiker and, if required, drop survival supplies. The drone returns to base for refuel or battery change and can repeat the mission until the operation ends. Looking at the functional and physical architecture of this device, it has several main parts and aims to capture data, then transmit data, then analyze data, then determine a match, which can be seen in the diagram on the left. To the right, we see some of the main components of this system. The flight control system, the sensors including camera and infrared, as well as a communications module, and the power system itself. So some sub-functions here include sensor activation, communication link establishment, ranger review, AI-based recognition, warning alerts, and a supply drop command. As for the diagram on the left. And each subsystem further reports and supports a defined set of functional requirements. Moving on to these functions, we see here the component allocation table. Several functions are assigned to their physical component and supporting components. And we see in these next couple diagrams how these operational processes are visualized through different flowcharts and tier diagrams. First, we see here phase 3, transmit and analyze drone data. Here, this phase demonstrates the way in which the drone captures photographs or video and transmits them to park rangers. The AI and rangers do the check of whether what the drone is looking at could actually be the hiker and confirm that. This next one, we see phase 4, confirming the hiker and communication location, and communicate the location of the hiker. This phase verifies information. In case of a drone confirmation of a hiker, the drone communicates with a ranger and then examines the state of the hiker and then is capable of dropping emergency supplies to that hiker. Finally, we will look at phase 5, refueling the LHD and repeating the search. In this phase, and in this tier flowchart, this section demonstrates the drone coming back to the base to recharge and the mission reinitiating again in case a hiker wasn't found, or if they were found, going back to the beginning. If they were found, they would continue searching. If not, eventually they would start over again. Moving on to the mission scenario. The mission scenario describes how the LHDS is used. First, park rangers receive a report of a missing hiker and identify a probable search area. Second, the rangers prepare the LHDS, upload the search plan to the system, and then launch the drone, initiating the mission. The drone then flies an automated search pattern while collecting video and thermal data during its flight. Next, potential targets are detected on board and by human operators in the command center, who analyze imagery from the device. Should a target be detected, the system focuses on that area and captures more detailed imagery for the operators to analyze. The rangers then confirm whether that imagery is the lost hiker or not, and thus validate the system. If the target is confirmed to be the lost hiker, the drone can then communicate with the hiker and, if required, drop survival supplies down to the hiker. The drone then returns to the base to refuel or change the battery and can repeat the mission until the operation ends. Next, the functional and physical architecture is displayed of the device and the system itself. On the far left, we can see that the system has main parts, including capturing data, transmitting data, analyzing data, and then determining a match, showing a large flow of data and how this system operates. It has several sub-functions, including sensor activation, communication link establishment, ranger review, AI-based recognition to recognize the hiker, warning alerts, and supply drop command to drop supplies to the hiker. On the right, we see some of the main components of the system: the flight control system, the sensors, including camera and infrared, the communications module between both hiker and operators, as well as the power system, which powers the system and device itself. The function is further shown by the component allocation table. This table shows how main functions are allocated to physical components. These functions include being prepared by the LHD, the deployment of the LHD, search for the hiker, detecting the lost hiker, confirming the hiker, communicating hiker location to the operators, transmitting drone data to the operators and the system itself, analyzing that drone data, refueling the LHD, and repeating the search until necessary, and completing the mission. These different functions are then assigned to their primary physical components and supporting components that were visualized. Some of these were visualized on the previous flowcharts depicted. Next, we'll look at some of the operational process flow diagrams. This first one is of Phase 3, transmit and analyze drone data. It starts with the LHD capturing data, identifying with the park ranger team, receiving data, and analyzing for a match with the hiker or not, and then ending that process. This phase specifically demonstrates the way in which the drone captures photographs or video, being of the hiker themselves or an object that isn't the hiker, but still data that it detects and captures, and then transmits these photographs and videos to the park rangers and operators for them to analyze for themselves. The AI and rangers do a check and an analysis and determine whether or not what the drone is looking at could be a hiker or not. This next operational flow diagram depicts phase 4, confirming the hiker and communicating the location of the hiker to the park rangers. It starts with whether or not the photographs or video that the system captured was an organism that matches the lost hiker. If so, it follows through several sequence of events until determining if survival supplies are needed, and if so, moving to the next step, or dropping supplies if supplies are needed, and if not, moving on to the next step. If it detects that there isn't an organism that identifies and looks like the lost hiker, then we'll go through different sequence of events, marking that the organism has been checked, but then continuing to move along with its search until it does find a hiker that matches the description. Finally, this final operational flow depicts phase 5, refueling the LHD and repeating the search. Following up with the last operational flow we looked at, determining if the hiker was found. If it wasn't, it goes through a sequence of events, determining if it had reached the operational range limit. If so, it had to keep searching. If not, it returns to the LKL land, the last known location land, refuels, replenishes, relaunches, and then resumes from its last step. If the hiker has been found, then the search has been completed, it's a success, and the operation ends and is complete.
And for this slide shows our requirements traceability metric. On the left, we list the top levels, stakeholder, and mission requirements. For example, the drone has to autonomously search a defined area, and it needs to detect a human in different weather and lighting conditions. And it should stay in the air for around 2 to 3 hours. And it must provide real-time location data and operate safety. Each of these high-level needs is then broken down into more detailed driving requirements. That includes things like having a manual override for the search patterns, setting a minimum detection accuracy, or triggering a low battery warning when only a certain number of minutes remain. In the final column, we assign a verification method to every single requirement, whether it will be verified by test, demonstration, inspection, or analyze. The main idea here is simple. Every stakeholder need is linked to a requirement, and every requirement is linked to a way of checking it. Nothing is left hanging. So for this slide, we move into risk management for the lost hiker drone system. In this table, we list our key risks, and we try to write each one in a simple, like if-then format. For example, if the battery depletes faster than expected, then the drone may have abort the mission or even crash. If the communication link drop out, then imagery and comments can't get through. If the detection algorithm misclassification object, then we might miss the real hiker and waste time chasing false arms. For each risk, we rate the likelihood and the impact as low, medium, or high. Then we add a proposed mitigation and planned verification method. So this table is not just a list of worries. Uh, it is the like I think starting point that tell us which risks matter most. What are we going to do about them, and how we will check that the solution actually work. And here's the risk assessment. We come up with a risk heat map. The horizontal else is the likelihood, and the vertical else is the impact. When we plot everything, risks like battery depletion, loss of communications, and detection errors all end up in the red zone in high upper right. Those are the items that are both quite likely and very serious if they happen, so that get the most attention from the team. Other risks like GPS interference, regulatory issues, or long-term sensors degradation tend to sit in the yellow area. They still matter, but they don't drive the design as strongly as red ones. The point of the picture is to make our priorities obvious. We don't pretend all risks are equal, and this heat map shows clearly where we need to spend our engineering time and money first. For the risk mitigation, in this slide, we zoom into how we deal with the highest priority risks. For the battery depletion, we don't just say we will be careful. We add continuous battery state monitoring and automatic return to home trigger when we hit the reserve level. And on the operation side, we plan flight time conservatively and keep spare batteries ready. For loss of communications, we introduced the dual link setup and the dedicated loss com mode. So drone knows what to do if the link suddenly drop. Operators are also required to run link check before launch respect range limit. For detection error, we allow the confidence threshold to be turned. Um, Also, we bring a human into the loop for critical detection, and we will keep improving the model with real mission data and sensors fusion. Whether Weather and GPS-related risks are handled in a similar way, a mix of smarter technologies and clear operational rules. So the main idea is every serious risk get both a design response and a procedure response. The combination is much more robust than relying on just one of them. So for the risk development process, we start with the risk identification. We look at the system from several angles, like basic field mode thinking at a component level, working through the whole mission timeline, launch to recovery, asking for input from people who actually fly drones or work in search and rescue. And the last one is checking each major requirement with the question, what if this isn't met? Next, we did a likelihood and impact assessment for each risk using a qualitative low, medium, high scale. We land on data where we had it and on engineering judgment where we didn't. Then we design a mitigation strategies, always trying to pair technical solution with operational procedures. And then we make sure every important risk had a verification plan. Some can handle with analyze and simulation, but the high consequence ones have to be excited in realistic text. So this process keep risk management connected to the rest of our system engineering work instead of being a one-time checklist. So for this lesson, we learned a lot. First, we realized how important it is to keep requirements and decide separate. Whenever we jump too quickly to a specific hardware solution, it becomes harder to change things later without breaking the logic of the requirement. And then building a context diagram and functional flow diagram really paid off. They forced us to think at a system level, who interact with us, what information flow in and out, and what actually happens at each step of the mission. And then the maintaining traceability turned out to be more useful than we expected. Being able to trace from operational needs to a detailed requirement and then to the test plan made it much easier. It is much easier to spot gap or vague statements earlier. Also, the writing tasks in a if and then format style made them much easier to communicate. Stakeholders immediately understand what could go wrong and what consequence would be. So for the last one, we learned the value of integrating with feedback. Comment we got on things like missing labels or mismatched inputs and outputs directly improve the quality of our diagram, tables, and race product. All of this lesson will carry out as we move toward to prototyping and eventually real-world testing for this system. Thank you.